Yes, good afternoon, everyone, especially those online as well as those in the room. My name is NITheCS Colloquium. I am from Quantitative Finance. And on behalf of Professor Francesco Petroccioni, it gives me a great pleasure to welcome Dr. Isobel Kolbe, who is going to talk to us about higher energy heavy ion collisions in the oxygen era. Dr. Kolbe, uh, he's a lecturer at the University of Wits and has a PhD in physics from University of Cape Town, and also has done some postdoc fellowship at Washington, the University of Washington, as well as in Spain. And her research is actually into physics and particles energy. And over to you. We're looking forward to your talk. Thank you.
Very much. Thank you. Thank you for the introduction. Thank you all for coming. Welcome. Let me just find my pointer. Very good. And thank you for the invitation to give this talk. I'm always very excited. But I see so it's always difficult to know exactly how to pitch these talks. So I was wondering if is there anyone in the audience who didn't do any physics beyond high school? No, you all did physics beyond high school. You have degrees in physics. You did some bachelor's degree in physics. Okay, I that means it's just a question about what the very first slide should be. So because actually I think a lot of the physics that I work on is not introduced even at undergraduate level, and so this is it's kind of fun and interesting because I think you can understand this physics. You don't really need a bachelor's degree in order to be excited about what's going on here. So what I'm going to try to do is tell you a little bit about the physics of heavy ion collisions. And then I want to introduce an open question in the field and one of the really exciting new experiments that are being done right now to try to answer those questions. So let's first start with the thing we know. We should all be sort of reasonably comfortable with this periodic table, right? One of the things about the periodic table, the reason I wanted to start here is because it's actually quite remarkable. Almost all of our daily experiences with things that we interact with around us, all the material around us and everything that we touch and work with, almost all of their properties can be understood because if you understand why the periodic table has the structure that it does. So you'll remember from high school that there are rows in this periodic table, and that has to do with the levels of the electrons. And then, of course, as you go along, if you snake along these rows, the nuclei of these elements become heavier and heavier. And what's interesting to me is that this means that you can actually understand all of that very complex behavior just by understanding one or two things about the structure of the atom. So you really start with this very incorrect picture of an atom, right? That we all know that there's an atom has a nucleus, which has protons and neutrons inside it, and then there are these electrons that go around it. And the remarkable thing about this physics, about this periodic table and everything, is that all of that physics is understood if you simply know something about the orbitals of these electrons. You know something about the orbitals of these electrons, and you know something about the number of protons inside the nucleus. Of course, there's quite a bit more to it, but you can get very far with just that picture. And we did for sort of maybe 100 or 200 years. That was the physics that we had. But it turns out, and this is not taught in high school, it turns out that in fact these nucleons inside the nucleus, the proton and the neutron inside the nucleus, these are not fundamental particles. You were probably told that's the smallest thing, that all of matter is made up of protons, neutrons, and electrons, and that's false. So protons and neutrons themselves have structure, and they have this structure in which it turns out that they're sort of made up of other smaller particles, which we call quarks. In this picture, there's these colorful balls are quarks, and they are held together by particles called gluons. This is a sort of a loose picture way to think about this, but the important thing to realize, to notice, is that the most fundamental particles in the world or in the universe are definitely not protons and neutrons. They can be made smaller. As far as we know, the electron is a fundamental particle, but so we did well there. But the nucleus is made up of not really protons and neutrons. It's really made up of quarks and gluons. So this then is the standard model of particle physics. It's sort of like the periodic table of particle physics. And you have here at the top, so let's see, so these purple things, these are the quarks. There are 6 different types of them: up, down, strange, charm, top, and bottom. If you're an Alice experiment, you would say beauty, of course, yes. So these are the purple, the matter particles that make up the quarks and that make up the protons and neutrons. Then down here is the particle that you will recognize, the electron. It turns out that there are heavier types of electrons. There's the electron, and then it's sort of heavier cousin, the muon, and it's even heavier cousin, the tau. And they have an associated particle, the neutrino. Each of them has their sort of associated neutrino. Those are then the matter particles, and then you have the gauge bosons that mediate the force. Part of the reason that we sort of structure it in this way is because although there are different ways to think about forces, there are different ways to think about interactions in nature. One of the easier ways to think about it for things like gravity is to think about Newton's forces, right? Newton's way of thinking of gravitational force. But it turns out that on this like particle level, actually, there's a better way to think about the mediation of forces. And it's really to imagine that there are particles that are exchanging other particles. And in this exchange, they are interacting with each other. So one way to think about this is if you sort of said, oh, if you imagine being on an ice skating rink with a friend of yours, and you're holding a heavy, those like heavy medicine balls that they always have in the gym. You're holding a heavy ball, but you're standing on ice skates, and you throw this ball to your friend, and you start throwing this ball back and forth between you, you'll start to move away from each other, apart from each other. So in that way, you are mediating a force by exchanging a particle. It's a loose analogy. It's not a perfect analogy, but just to sort of say that is the mathematics that we use here for the standard model of particle physics. It's written in terms of these particles that exchange bosons. So here's the gluon, which we will keep coming back to the gluon. This is the one that sort of mediates the force that holds these quarks and quarks together. Here's the photon, which you might recognize. If you follow some amount of particle physics, then you will know that we sort of think about light as being carried by individual particles called photons. Okay, and then there's the Z and the W, and these have to do with nuclear decay. I won't talk too much about it. The last thing I wanted to say was that there's this sort of Higgs particle as well, which is, if you follow particle physics, that's the sort of the big famous discovery from CERN, was in 2012. But I won't talk much about that. What I really wanted you to be sort of comfortable with is this idea of there being quarks, and the quarks are held together by gluons. And now I want to sort of dig into this a little bit further. These quarks are not really your sort of normal way of interacting with each other. The strong nuclear force, which is the force that governs the behavior of quarks, has the opposite behavior to the electromagnetic force in terms of its strength over a distance. So you will know that if you have magnets, if you bring the magnets closer together, the strength between them becomes stronger. If you take them further away, of course, the strength between them becomes weaker. The strong nuclear force has the opposite effect. When you start off with two particles that are close together, two quarks close together, their interaction with each other is very weak. And if you try to pull them further apart, as the distance increases, the strength of the force increases as well. So quite counter to what we're used to with electromagnetism. And the way to think about this is this sort of picture that we have here. If I start off with two quarks that are, say, bound together in some kind of a particle, if I wanted to try to separate them, suppose I wanted to see one of the quarks alone, I try to pull them apart. As I'm pulling harder and harder to pull them apart, I'm putting more and more energy into this. And E equals mc squared. Einstein says E equals mc squared. At some point, you put so much energy in that you just produce two more quarks. So this energy that you are putting into pulling them apart gets converted into matter, which means that, okay, it's fine. You have separated your two first quarks, but you still don't have an individual quark in nature. You still cannot see one quark by itself. And this is a sort of a fundamentally important aspect of the strong nuclear force, is that you cannot separate quarks out from each other, which means that you cannot study them individually. You cannot study, it's very, very difficult to study the behavior of individual quarks because they never appear in nature by themselves. Good, okay, so that's the important part. Let's just recap quickly what I was saying. The first thing that I said was that protons and neutrons have structure, so that's an important message. And the other thing is that quarks and gluons are confined. So quarks and gluons are confined within sort of larger particles. Good. This is supposed to be a nuclear physics talk. Why? So we haven't talked about the nucleus very much yet, but I'm going to put nuclear physics in quotation marks because it is only nuclear physics in the sense that we work with nuclei. We do not study the nucleus. We don't actually study the structure of the nucleus. We don't study the makeup of the nucleus. And I will take that statement back at the end of the talk as well. But good. So this is nuclear physics. Why do I want to do this? Now, I've said to you that I cannot separate the quarks out from each other. But I did also say that when the quarks are very close together, they behave as though they're free. Their behavior, the force between them is very weak. And so when they're close together, they behave as though they're free. So paradoxically, a good way to study the way that individual quarks behave is to put as many as you can in a small space. You put many of them very close together, and then you have a large space in which these quarks are behaving as though they were free. And so this is what we want to do. That's the argument that I would give a physicist. But if I have to apply for funding from the government, I will give the following argument for why we want to do this. And it is that we would like to study the early universe. We'd like to study the nature of the universe a microsecond after the Big Bang. And why is it that you have to do it this way? So here's a picture that you know about the sort of, here's the Big Bang, and there's the expansion of the universe. It cools down. At some point, you get this cosmic ray, the cosmic microwave background, which is the furthest back that you can see with the telescope. And then this sort of expands even further. At some point, you get the formation of stars and galaxies, and then you get all the way to the end here where we are now, where the universe is cold, and we can sit and think about this stuff. What you can do to try to understand the evolution of the universe is you build a big telescope and you look further and further back in time. But you are limited by this cosmic microwave background. You cannot see behind it. Why is that? So we can start off by thinking, this is the way that the universe is here now. It's very cold. It's governed by Newtonian gravity. There's some general relativity, but there's really actually the forces that shape the universe. That's it. And it's cold in the sense that it's the average temperature of the universe is like 3 Kelvin or something. Okay. If you go further back, when you hit this cosmic microwave background, you start to find that, okay, as I go back in time, the universe is getting hotter and hotter. So at some point, the temperature is so high that this picture that I had of an atom, which had a nucleus with some electrons going around it, that these electrons, everything is now so hot that these electrons cannot bind to the atom. So they start to drift off. And then you get an electromagnetic plasma, right? You have a material which is made up of moving charges. The sun, for instance, is an electromagnetic plasma. It's a plasma thereof. There are these electrons moving around everywhere. There's the reason you cannot see through the sun. One of the reasons is, of course, that it's producing a lot of light, so a lot of particles coming at you. But that's not the main reason that you cannot see through the sun. The main reason you can't see through the sun is because photons cannot travel through the sun. Photons that are produced at the center of the sun. Does anyone know this fact? Did you know this fact? Would you like to hazard a guess how long it takes a photon that is produced at the center of the sun to reach the surface of the sun? How long? Order of magnitude. Seconds, days, years? Many, many years, millions of years. It takes millions of years for a photon to travel from the center of the sun to the edge of it. Then it only takes 8 minutes to get from the sun, the surface, to here. And that's because it's moving through this plasma. So the electrons are absorbing and re-emitting these photons the whole time. So the photon cannot go through. Okay, good. So that's an electromagnetic plasma. That means that we cannot see behind it. Can't build a bigger telescope to see earlier into the history of the universe. So you want to go further back, but you start to run into other problems. So at some point now it's so hot that the nucleus cannot bind. So now you have freely moving quarks, protons and neutrons. And then of course, at some point it gets so hot that the protons and neutrons themselves cannot bind. And now you have a soup of quarks and gluons. This is at a microsecond after the Big Bang. So 10 to the minus 6 seconds after the Big Bang. So we're over here. And oopsie. Okay, oh, well, okay. You might want to, you might simply ask the question, how can we learn something about the very early universe? We want to understand the evolution of the universe. We want to know what matter was like, how these things came to be. How do we study that? And you cannot study it by building a bigger telescope. So in fact, what you try to do is recreate this environment on Earth. And so this is what we try to do. That is the argument I give to the NRF. The argument to a physicist is, it's cool. It's very cool to study this material simply because it's interesting from a perspective of nature. So how do we do this? This is just a picture of the Large Hadron Collider. This talk will be a little bit focused on the Large Hadron Collider because of the interesting physics that I want to tell you about later. But there is another particle collider in the US. It's a slightly smaller one, but this is the biggest one in the world. So it's got a 27-kilometer circumference. It's about 100 meters underground in Geneva. So this is Lake Geneva over here. And then over here for scale, you can see the airport in Geneva. So that's a runway. And you've got the Alps back here with Mont Blanc up there. Good. And here's this whole ring, and there are some large experiments everywhere. And the way that you do this is there's an enormous set of accelerators at CERN, it's an accelerator complex really, and you start to accelerate particles in one of these accelerators until it goes to a nice high speed, and then you put it into a bigger accelerator, it goes like much faster there, and then put it into a bigger one, and it goes much faster there, and at some point you get into the Large Hadron Collider. And these are accelerated, so it's a circular accelerator which uses superconducting magnets to accelerate the particles, and then at strategic points along the ring, you have places where you just use your magnets. So you have one going around one way, one the other way. You just use your magnets to direct those two beams at each other. And then they will collide here. And if you're clever about where you do this, you build a very large detector around that to see what comes off. Good. So here's an animation of what this looks like. So here's maybe some sort of lead nucleus coming down the beam. I have underground this enormous detector, which is wrapped around the beam. And then I do the collision over here, and it produces lots of particles. It produces 10, 20, 30, 50, depending on the energy, 100,000 particles. Each of these colorful lines is the path that a single particle has tracked through the detector. And then they leave energy deposits. These yellow towers are energy deposits in the detector where you sort of measure how much energy a particle had. Now, you see almost immediately one of the big problems that you have here is that despite the fact that these detectors are very sophisticated, you actually don't get very much information from them. You get only that there was a particle and where it was and how much energy it had. Some of the detectors have been able to sort of really be very sophisticated with that information, then you can sometimes tell what kind of particle it is, but not always. And so now you are stuck with this information. How do you study this thing which you have now produced? You create this collision, you produce some plasma, it lives for a tiny, tiny, tiny amount of time. The only thing you have to study is these particles that come off. That's what I do. So I'm not an experimentalist who looks at how to understand what has come out of these detectors. I just try to think about, once you understand a little bit about this mess here, once you understand that, what can we learn about nature from there? So we have to model this quite carefully. So we start off with what I wanted to do here is to sort of express to you how complex this system of modeling is that has to happen. So you start off with, here are these two colliding nuclei. So I start off over here. They are Lorentz contracted. It's not really important if you have some physics background. This has to do with the fact that they're moving almost at the speed of light, so they are contracted in the direction of their motion. But okay, that's not so important. Once you now collide these two nuclei, you produce these particles. How are they produced? We have 2-to-2 scattering. You scatter particles in each nucleus. Particles from this nucleus and particles from this nucleus will collide, and they will produce particles that come out. But these things that are coming out are not in any way in equilibrium. They are produced in a wide variety of energies. They are moving in all kinds of different directions. But strangely, and it wasn't expected, but it is true, it turns out that there are so many of these particles and they are interacting so frequently that they thermalize very quickly in some sense. So in some way, it reaches some form of equilibrium, which means that you don't have to be talking about the physics of billiard balls that are moving around. You can start talking about the physics of a fluid. This is much better described by a fluid. Just as we use thermodynamics to think about water, to think about like the temperature, pressure, that type of thing, volume, those kinds of quantities are things that we talk about fluids, but we also know that water is made up of molecules, and you can get to a lot of these ideas of pressure, for instance, by thinking about a molecule that is bouncing off a wall and so on. Okay, so we will then use at some point it thermalizes, and then you have this quark-gluon plasma phase. So it's a plasma that's made up of quarks and gluons. The quarks and gluons are moving around freely, and the best description that we have for that is a hydrodynamic description. It is to be sort of technically correct, in case anyone is in the audience who would like to know, it is really relativistic viscous hydrodynamics that we use. And so it's not quite exactly the thermodynamics that you use in high school. Okay, at some point, this plasma now, so you produce this plasma, it's very hot, it's very dense. It's 100,000 times the temperature of the sun. It's got 20 times the density of normal nuclear matter, and outside of it is vacuum. So anything that hot and that dense will expand very rapidly into this vacuum. So it expands really, really rapidly. But what did we say about these quarks and quarks if you try to pull them apart? So this plasma is expanding very rapidly. You cannot pull the quarks apart. At some point, they don't want to be far away from each other, and they hadronize back into these normal everyday particles that we know, the protons, neutrons, pions, that kind of thing. So that's this hadronization phase. And then, okay, the rest I will sort of not talk too much about because it's not so very important for the present discussion. But what happens is these hadrons then go off and into your detector. And this here is then an image from a detector where, again, the collision happened here in the middle. And then each of these lines is a particle that has tracked its way through the detector. Okay, so we have to do this modeling. What do you get? Once you've done this, you can sort of come up with kind of a nice model. I just want to show you this. I'm just going to try to make it go a little bit slower because it's very fast. So this is from a model that I work on as well. It's called Triectum. It's probably state of the art. What you are looking at is, now I'm looking down the beam. I've collided the nuclei and I've deposited all of this energy. So there's a temperature bar on the right-hand side here. This is a temperature bar, which has now sort of disappeared. Good. So you can see that there's like hot spots, cold spots over here, and this thing is expanding very rapidly. And then what we've written out here is when the fluid has hadronized into particles. So now you see that as time goes on, after a while, you just have lots of particles. And you see the space scale is changing on the X and Y axis. So we're really zooming out. And you will see that these particles sort of move out into the detector. This is a state-of-the-art model. It contains all of the steps that I've just showed you before. It contains the physics of what does this nucleus look like? How does it thermalize? How do you evolve it? How do you evolve the fluid time of this? And then also the hadronization and everything moving off. Okay. Now, let's talk about this plasma. How is it that if this thing exists for such a short period of time, how can you tell, how can you know for sure that you produced it? Because you can't see it, right? Its lifetime is on the order of 10 to the minus 28 seconds. Now, 10 to the minus 28, if you think about that carefully, the speed of light is 10 to the 8 meters per second. Even if your nearest detector, Siggy, sorry, I never know, the nearest detector to the interaction point is a couple of millimeters away, right? 1 centimeter. Let's say the nearest detector is 1 centimeter away. Even if you knew exactly when that collision was going to happen, and at the moment that that collision happened, you turned on a laser that shone some light from your nearest detector, a centimeter away, by the time that photon, which is moving at 10 to the 8 meters per second, by the time that photon gets to your plasma, the plasma hasn't existed for a billion times the length of its own lifetime. It's like trying to take a camera now and be like, I'm going to take a picture of a dinosaur. The dinosaur hasn't been around for ages, right? So how do you study this? And what the sort of basic argument has been is that, okay, you see all these particles that arrive in the detector. You need to convince yourself that you see signatures of this plasma, that there's behavior of these particles that you cannot describe in any other way. And there's sort of some standard picture that really you want to know. You want to see the low momentum physics. You want to see that the low momentum particles, this fluid stuff is happening. You want to see the high momentum physics over here. And you have to have a control experiment. Any good scientist will tell you that you have to have an experiment in which you don't create the plasma, where you can look for these same signals and see if you create the plasma or not. Okay, so let's see what we do. Before we do this, I'm going to have to introduce 3 pieces of jargon to you. They are 3 words that if you don't work in this field, you will not have known them, but I think that the physics of it is reasonably simple. And so I would just warn you that I'm now going to teach you 3 jargon words. Okay, let's do them one at a time. The first one is centrality. You don't have to worry about the plots at the top. What I just want you to know is that it matters when you do this, when you take a lead nucleus and you collide it with another lead nucleus, it matters how central that collision is, how head-on is it. So it matters whether you collide maybe you collide almost completely overlapping, or maybe only some sort of peripherally, or maybe ultra peripherally in this way. It matters, but you cannot measure it. You cannot know. It's very important, but you cannot event by event know what the centrality was. There's no way to control it, to say, I'm only going to do head-on collisions, or I'm only going to do peripheral collisions. There are collisions that are happening millions a second that are happening, and you just get all of them. So it's important to know what the centrality is, but you don't immediately know event by event. What you can do is use a plot like this. You can look at the whole set of the collisions that you have, and of course you presumably you would produce more particles if you had a very head-on collision, and fewer particles if you just had a peripheral collision. So you try to sort of map these things out and connect them to each other. Good, that's centrality. The next one is flow. This is the one that we're going to use to prove that the low momentum signatures of the plasma are there. What this comes down to is that if you have a sort of semi-peripheral collision, so you collide a lead nucleus like this, but slightly off center, you see that you create an almond-shaped region. The plasma that you create is not a round plasma, it's an almond-shaped plasma. But again, I remind you that over here, the density is 20 times normal nuclear density. Over here, it's vacuum. So what's going to happen is that it's going to expand in this direction and in that direction. But because it's oval shaped, so it's not round, because it's oval shaped, it expands much faster in this horizontal direction than in the vertical direction. So this is something that we sort of say, the technical words are you take your position space anisotropy, this almond shape, and it is converted into momentum space anisotropy. And the reason this is interesting is because you can only get that with the fluid. You can only get that if you are really talking about something that is not just a bunch of billiard balls moving around. You really need that it has to be a fluid. So the only way you get this is to have a fluid. And you see this in the data. It was almost one of the first things that they measured was that you see that if I measure as a function of the angle, I see that I get lots of particles in one direction and fewer particles in the other direction. And that's the most important thing. We won't talk too much about flow, but I wanted to let you know because we will sort of mention it again. The key thing to take away from this slide is this V2. So the real question is going to be, once I sort of extract how curved this line of dots is, I can extract a value that tells me how curved that is, and that's the V2. So we will come back to that, but that's the most important thing here. Good. And then the last piece of jargon, which I will really try to dig in a little bit, is jet quenching or particle suppression. This is on the high energy side. So now I say, okay, fine, I have a plasma and I produce some particles in this plasma. These particles move through the plasma and interact with the plasma and lose energy, like a rugby player that's running through mud. And you can tell how tired your rugby player got, or you can tell by how tired he got. You can tell what he ran through. Did he run through water? Did he run on grass? Did he run through deep mud? So you can learn a little bit about your plasma if you know a little bit about how particles lose energy. So we sort of imagine that when you produce these particles, you always produce them sort of back to back. E equals mc squared, but you have to conserve momentum. So you always produce these particles back to back. And maybe one of them travels only a short distance in the plasma and the other one travels a long distance and loses lots of energy. And we see this in the data immediately. Here's an event display from Atlas, from the last run 3 of Atlas. And you see that I have back-to-back jets here. And on this side, I see that this calorimeter tower is very tall. Lots of energy was deposited here. But right behind it, there's nothing in these calorimeter towers. These calorimeter towers are completely flat. You wouldn't be able to tell that there was a particle that had gone in that direction. And that's to say that, but I know that this particle had a friend behind it. So it's disappeared in the plasma. It's completely lost all of its energy. I do want to dig down into this one little bit more. I wanted to teach you this observable called the RAA. It's not really important to understand all about it, but it's important to see that it's less than 1. So it's a number that we use to say how much, if you have some number of particles with some energy, how much energy did they lose compared to an experiment in which they wouldn't have lost any energy. And so you take some ratio, and the point is that if this number is less than 1, then there is some energy loss. And if it's not less than 1, then you haven't lost energy. So what I'm going to look for in this RAA observable is that it's less than 1. Okay, let's do a quick recap of these 3 jargon things. I had centrality, which it's important to know whether things are overlapping. Then I had flow. There's this observable, we'll call it V2. The only question there is it 0 or not? Do you get some modulation or not? And then we had jet quenching, where jet quenching is how much energy do you lose in this plasma? And we use the RAA to measure this, and we want to know whether it's less than 1 or not. Good. I almost want to stop for questions. Is that allowed? I'm not sure. Okay, good. Okay, let's get back to this question that we had at the beginning. How do you discover the plasma? You want the low PT signature, the flow. You look for the flow. You want the high PT signature, which is this energy loss. And then you need a control experiment. So you do these things and it's fantastic. And you turn on your very expensive machine in Switzerland and you do it and you do the measurements and you see the V2 is there and you see the energy loss is there and you're like, this is great. Perfect. Let's just quickly do a control experiment. Let's just quickly double check. Let's just double check a few things. So they did this lead-lead collision, which we had over here, and they saw the low PT, the high PT, fantastic. And then they did this control experiment. They actually did it for slightly different reasons, but in the end, it was supposed to be a control experiment. What they did was you take a lead nucleus and you collide a proton into it. Just a proton, just the nucleus of a hydrogen atom, yeah? You collide a small proton into this lead nucleus just to see whether you have everything under control, because there shouldn't be a plasma. You haven't produced lots of particles, so you should not have a plasma. And they do this control experiment, and they very quickly realized that you had a small problem. And here's the problem. So I'm showing you now these two plots that you understand perfectly, right? On the top is the RAA, the energy loss. This is the one that we're going to ask, is it less than 1 or not? And in the bottom, I've got the V2. This is this flow question. Here, I'm just asking, is it 0 or not? And for the experts in the audience, if you're, if you would like to take a short 2-minute nap, you can. But for the experts in the audience, I think it's important to say that we actually understand the physics of this very well. We understand that in this low PT region, this V2 comes from multiple interactions. It's a strong coupling. In this intermediate region, you find that you transition into a kinetic region where you're managed, where the physics is really that of kinetic theory. And then at the high PT end, you see the energy loss. So you see here that the sort of the V2 comes down, but there's a high PT V2, which we think of as a path length dependent energy loss. And here, the RAA on the top plot is less than 1, so there is some energy loss there. Okay, if you took a 2-minute nap, I'm going to ask you to come back. So the question was, this is for lead, and I see everything is nice and it fits so nicely. I see the physics of the low PT stuff in here, this low momentum stuff, the fluid flow is here, and I see the physics of the high momentum stuff over there. But this picture is not so simple in proton lead. In proton lead, I have a really strange thing happening. So I've got again here, essentially the RAA on the top and the V2 at the bottom. And I see, okay, fine. I see all the same physics for the V2. It rises and so forth and comes down. And there's this high PT tail over here. But the first thing that is confusing to me is, if there's no plasma, where is this V2 coming from? This is a non-zero V2 over here. And if there's no plasma, where is that coming from? But in any case, maybe that means there is a plasma. So if there is a plasma in this proton-lead collision, then remember I said I have to see low PT and high PT. So let's have a look at the high PT. And so then I look at this plot at the top and I measure the RAA and I see that, okay, maybe things are a little bit off. Maybe I could draw like a squiggly line through this. But actually the truth is that that is as close to 1 as you can get. In fact, they have, oh no, not on this plot. Sometimes they put in the error of how well they know where 1 is. And even that's very small. So we know for sure that in proton lead, there is a non-zero V2. There is definitely something flowing in V2. There seems to really be this. It's almost impossible to argue with that. There seems to really be something flowing in these proton lead collisions, but there is no energy loss. And you can, what I work on and what the group at UCT works on is to really try to understand, where is this energy loss? What is happening? Why can we not see this? And the first thing that you should realize, what you should think about as soon as you find that you run into an experiment with a contradiction, is that you immediately should say, you should remember that nature has no contradictions. There are no contradictions in nature. If you run into a contradiction, you have made a mistake. You've done something wrong. But the question is, what have you done that's wrong, that's not right? What have you not understood? And one of the problems, which we don't have time to go into, is that this proton-lead experiment is not great. It's not a very good experiment. It's a very uncontrolled experiment. So what some friends of mine suggested to the LHC a couple of years ago was that, oh, you should just do something else. Do a more controlled experiment. Do this oxygen collision, because an oxygen nucleus is much smaller than a lead nucleus. But because it's not so uncontrolled with this, because it's more symmetric and that type of thing, you might get much better results. You might be able to understand the physics much better. So I took the slide from my friend Alexas, who was involved with this from the start. He was a postdoc at CERN in 2018. 2018 was the year that I submitted my PhD a week before getting married. So in that year, they thought, oh, it might be a good idea to do the oxygen run. Then a couple of years later, they had this workshop, opportunities in proton oxygen and oxygen. And then here's the truly remarkable thing was in 2024. So last year in November, they had a workshop at CERN where they had, at that stage, they had managed to convince CERN to run oxygen. But so they had this workshop there and they sort of are saying, oh, it's very interesting physics. We can do all of this. We can do all of this. We can do all of this. In November, they have this workshop. In July, so that's the next thing here. So in July of 2025, now July, a couple of months ago, they ran this experiment. They actually did the experiments at CERN, which is quite extraordinary. If you think about it, like how often in your life do you know people who sat down at a table and said, oh, this is really cool physics. I wonder if we can get the largest, most expensive experiment in the world to do it for us. So they managed to convince them to do it. They did the experiments in July, and then in September we had the first results. That in itself is quite spectacular. Anyone who so there's an Alice experimentalist here, but if you speak to any of the experimentalists who work on these large experiments, it can take years to get results after you do the run. So this, you take the data. To give you an idea, Alice produces 3 terabytes of data per second in real time. Then this data has to be processed. A lot of it is processed like down in the tunnel already before it even comes out on top onto like onto dry land. I almost said, before it comes up. Then it has to be cleaned up and analyzed. It can take years to get this data. These guys worked throughout their entire summer holiday and got us results. The run was in July and we had results in September. It's quite spectacular. They worked really, really hard and it was extremely exciting. So I was at this conference in Taipei and we got the results there. But what we wanted to do, of course, was just have some predictions before the results came out. So here's with that same triectum. You have oops, what's happening? You have a lead collision on the left-hand side and oxygen on the right, just to give you an idea of like the difference in size of these systems. So on the left-hand side and this is with it's with triectum, so it's really state-of-the-art cutting-edge modeling that's happening there. And what I wanted to show you on the right-hand side here is this is the point. This is why oxygen is interesting. So oxygen, here's as a function of the number of participating nucleons, you see that oxygen sits here, right here, very close to sort of peripheral lead, so a small system, but also quite close to proton lead, to central proton lead. And so traditionally, you might think that these systems are in some ways the same size. So that's kind of interesting. Here's the model that I work on. I think I will skip this because I just wanted to say that we can do this high momentum energy loss in this model. We can do this very sophisticated triectum stuff in the background and then put the jet on top. And here are the predictions for this result. So here's an event display from the oxygen run. You look at this date, the 5th of July, 2025. And that's so exciting. Okay, so this was the oxygen run. It's an event display. So you see a very central oxygen collision here with lots of particles that came off. And here was our prediction for the RAA. So we suspected the red is oxygen, and then the yellow over here is neon. That was the prediction. Very good. Here is the result. So they showed, we got that prediction out on Thursday. On Monday at the conference, they showed this result. And what I'm showing you here again is the RAA, so the energy loss. And so the blue data points, these 4 plots are all the exact same blue points. So the data is exactly the same for all 4 of them. But if you look at the top left, what they've overlaid is some theoretical models that have no energy loss. So if your model has no energy loss, then you see that, okay, you get something that's close to 1, but it's not obvious that it's always 1. There are some sort of systematic uncertainties here. But okay, the data seems to be very significantly below what those models are predicting. And then, so that's on this left-hand side here as well. On the right-hand side, you see models that have energy loss in them. And you see, okay, there's like lots of them. What's incredible about this, though, is that these results were all out before the experimental data came out. So these are real, genuine predictions. They are not tuned to fit the data at all. And I wanted to specifically point out that there are 2 curves on here that are by South African research groups. So my group did this one, this yellowish light green one, which sort of goes off there. We understand why that goes off. We did pretty well, actually, over here. And then there's a group at UCT that did this curve. So it's this gray curve over here. And this prediction that came out there. And also very, very close to the data and very good. And I think the thing to say here is that if you think back to the earlier part in the talk where I showed you all these different stages of the modeling that have to go into this, it's really remarkable that modeling has reached a level which is so sophisticated that you can put out a prediction, these kinds of predictions that do this well without having to tune the theoretical models at all. You really, the level of understanding that we have of these plasmas and of these collisions has reached a very, very sophisticated level. And I think we should, as a community, be quite proud of that. The other thing I wanted to say is that this is quite exciting because it seems very clear that there's energy loss here. So the flow is, of course, it was there. Everybody expected it. It should be there. It's in proton lead. Okay, fine. It's everywhere. But it wasn't actually obvious that you would produce a plasma in an oxygen collision. So, and this seems to be sort of almost irrefutable evidence. But There are still several things that need to be happened. They need to measure a few other observables that are also important, which I've left out. So it's not, I wouldn't say quite a discovery yet, but it's kind of exciting. Okay. Then I wanted to just quickly say have the last slide be much more technical, just in case that's sort of interesting to people. The modeling is so sophisticated that we can actually do other things completely. What I'm showing you here is different curves for, okay, so what we have done here is the in-plane over out-of-plane ratio. So we're just asking how much energy do you lose if you go along the short distance versus the long distance. But if you ask the question, does this energy loss depend only on the length of the path that you travel, or does it also depend on the temperature of the medium? So that's the difference between the left-hand curve and the left plot and the right plot. The left plot shows that if you consider this energy loss to only be dependent on the path length, and on the right-hand side, if you consider this energy loss to be dependent on the temperature as well. And then the key here is that the difference between the different curves is for whether you modeled how you modeled the size of the nucleons in your original colliding nuclei. So when you take your two oxygen nuclei or lead nuclei, or I think this is for neon. Yeah, we did this for neon. You can vary in your model the size of the nucleon and the size of the constituents of the nucleons. And that's what the difference is between these curves. And in fact, the modeling is so sophisticated that you could, in principle, extract this now from data. You can really see a difference in the way that, in how important that part of the modeling is, and whether it should depend on the temperature or not. So that's kind of exciting. That's what we're hoping to see. That's a bit much more difficult measurement to make. We'll have to wait a while for that measurement to be made, but there are some interesting other theoretical problems that we can pull out. Then the very last thing I wanted to say about this is that these oxygen collisions are not just interesting for us who care about path length dependent energy loss or whether the plasma was produced in oxygen. They're also important for other things. So on the left-hand side, I'm showing the modeling that goes into the neon nucleus. And what you see is that actually in these collisions, we can start to eke out the nuclear structure, the low energy nuclear structure. So in other words, what we need in this modeling, when we do the full modeling, we always need to know what the nucleus looks like that we're colliding. But low energy nuclear structure people are able to calculate that. And so they can calculate that and make predictions that are very difficult to measure in low energy nuclear physics experiments. And in fact, it turns out that you can do this kind of experiment, a very high energy nuclear experiment, and you can extract other parameters and make quite a bit of inroads into that. And then on the right-hand side here, I'm showing cosmic rays. So cosmic rays have to do with, it's actually very cool physics. There are particles that are coming from somewhere, we don't know where, but they are hitting the atmosphere, the Earth's atmosphere, and creating a shower of particles. And some of these have an enormously high energy, like really, really, really high energy, so high that it's almost impossible to imagine where they're coming from. We also don't know what they are. We don't even know whether the stuff that's coming in here is protons or lead nuclei. So, and they require quite a bit of modeling as well. But the air, the atmosphere that we have has quite a bit of oxygen in it. And so we can inform quite a bit of that modeling by doing these very controlled oxygen experiments. And that will help with the modeling that they have to do for their showers. And so it's really exciting to see the scope of the Large Hadron Collider move beyond just particle physics. It used to be, we just do particle physics, we just do Higgs, we just do quark-gluon plasma, but actually this physics is expanding much further. And South Africans are doing quite a bit of fun work there. So that's kind of exciting. And I think that's it. That's it from me. So just some take-home messages. If you came here and you didn't learn anything, I don't think that's possible. But something to just remember is that protons and neutrons have structure, and we can study the elements of that structure. We can recreate some of the conditions of the early universe, like right here on Earth, several million times a second. And there's a very active heavy ion program in South Africa. So we do both theory and experiment. There are groups all over the country doing really exciting work. And that is very sort of competitive internationally. And if you want to be part of it, you should just like reach out and find out. And then lastly, the future of these light ion runs is very exciting. So we will have a workshop at CERN at the end of the month to decide what to do next year, because now we've proven that this is interesting physics. So what else should we collide? Should we do, we could do argon, we could do germanium, we can do helium. So what should we do? What's going to be exciting? And it's really, sorry, protons. No, we do lots of protons. Why would we do more protons? We should do fewer protons for sure. No, this is being streamed. Okay, so good. it's an exciting time, and if you're interested to know more, please feel free to reach out to me. But thank you very much for listening.
Thank you very much, Dr. Kolbe. Any questions in the room? Okay.
Thank you very much for your talk. I'm sorry, this is a very naive question. The shape, the trajectory of that particles move in the accelerator is a circle, right? So the question is, I actually have two questions. One is, how important is it that this circle is a perfect circle? If it were not a perfect circle, would it kind of give some error in the measurement of results of the experiment? And then the second question is, when you have this picture where the particles, when they collide, they are emitted, if they're in an enclosed area, I know this is a very naive question. If they're in an enclosed area, how can they kind of penetrate the enclosure?
Okay, so the first question is about the shape of this ring. I am not an accelerator physicist, so I don't immediately I don't want to say anything too strongly, but the shape of the ring itself is not so important for the experimental result. The shape of the ring is important for how fast you can get it. But at all of these interaction points, in fact, the ring does sort of wobble, right? So you have say, suppose you had only one experiment, you would have one beam going one way, the other one going the other way, but you have to make them collide. So at some point they have to cross as well. So then they go, and then it goes into the other pipe. So that shape has no effect whatsoever on that. It has, I think it purely affects the amount of energy you can get out. The experiment itself is really just where these collisions happen, and these collisions, right? So that answers that part of the question. And then the second one was what these particles are produced, and they're in an enclosed space. Where do they go? It's not really an enclosed space; it's vacuum. The collision happens in vacuum, but it's really minutely small. These detectors that I have shown you here, so maybe I can try to go. I seem to have frozen. Just looking for a particle, a display. So the collision happens right in the middle here. This is not really an enclosed space. These are layers and layers and layers of different detectors, and these particles are moving through the detectors, depositing energies in some ways and so forth. So they're moving out. And okay, what is also true is that at some point, you're right, you hit the rock. Yeah, so at some point you hit the rock of it, and there are some, as far as I know, like especially down in the direction of the beam, they have several absorbers and so on, because a lot of the stuff is radioactive that's coming out there. So that's true. But as far as the physics goes, this what we're doing is looking at the information that these particles are leaving in all of these different layers of the detectors, which I'm also not quite an expert on.
I have a more technical one. In your model, especially the flow, how do you estimate those parameters like V2, and do you have sort of like an optimal parameters?
Very, very nice question. So, yes. So this model specifically, Triectum, so you're right. You have several elements to this model, and each of them has several parameters. And you can ask, how do I tweak these parameters? And what they have actually done is a full Bayesian analysis of over 2,000 data points. So it's interesting mathematics. You have several data points, and you try to fit your model to this. So you have you try your best to fit, and you write a little bit of like sort of light machine learning, in fact, that does this, and you find the fit for the data that fits all of the data the best, the set of parameters that fits all of the data the best, and then you are left with this set of parameters, which they also, this code, in fact, I should have said that this Triectum code is freely available. If you want to download it and play and run it, you're absolutely able to do that. And they publish every paper that they publish with, they put out with that the set of parameters that they used, so that you can perfectly reproduce their results. But the V2, for instance, is not. The V2 is an observable, so you run your model and you extract the V2 from that. Yeah.
Thank you.
Yeah. Cool.
Any other?
Thank you.
Okay, all right, like this.
Yeah,
Okay,
perfect,
sorry.
thank you.
I need some help with the mic. Yes, thank you for explaining the basics as well at the beginning. I'm fascinated by what you've described as this community that is working on this together internationally and seems to have so much momentum, excuse the pun, in this field that is creating a very special set of circumstances to advance science in this way. Can you talk a bit about how this was formed? Is it quite a formal structure, or is it more organic in its way? Does everyone, as you've encouraged people now to take part in this, is this something that it was set by a specific government, or is it just organically people that are doing the same thing, that like each other and like doing the stuff together?
That's such a lovely question. Thank you for that. It's because it's one of my favorite things about CERN is that, okay, so the short answer is all of the above. Both things have happened. There are formal structures within which people work, and there are people who work sort of more organically together. The longer answer is that sort of shortly after the Second World War, CERN was formed to do peaceful nuclear research across countries with many member countries. And today, I forget, Siggy will know how many member countries there are of CERN. South Africa is not a member country, but it's something like 50 or whatever, some enormous number of countries. And so then how this works is you become a member, you have to pay some percentage of GDP to the experiment, and then they run it, and it's great. And what this means is, but there are also people who work on this experiment who are not just from Europe. CERN is the European Center for Nuclear Research, but there are people who work there from all over the world, South Africa as well, but some South African countries. So we are there, Morocco, Egypt, but then also places like the United States and India and Russia and Ukraine and Israel and Palestine. These countries, people go there and they work. And so we've recently now, Russia has recently left CERN, but it's really an extraordinary thing when you walk around there and you walk in the cafeteria and you hear everybody discussing this physics in every accent imaginable. They're all talking, and it's a really incredible feeling. And good. So that's CERN. Within CERN, these large experiments, they are really quite big. They can be 2,500, 3,000 author members on each paper. Each paper has 3,000 authors on it, because they genuinely have this. There's a culture where you have contributed and you are part of this machine, and you are expected to help maintain it, help run it, help do these things. And it's not this sort of these glory days of the individual scientist who sat and an apple fell on his head and now we all revere him. That time is over, and people work really fantastically together. That's the experimental side. On the theory side, we don't have these formal structures, but an organization like NITheCS helps a lot with that. So it really helps to have theorists work a bit more organically. We don't have to be members of CERN to access the data and so on. So we work a little bit more organically. But I think that culture that is driven by CERN of really collaborative efforts across cultures and across countries, that seeps into the theory community as well. And so I'm working with a bunch of people at CERN, and people are working, I have, everybody's collaborating across the world, and it's really fantastic. And I think that that's something that we should bring into our other parts of our lives as much as we can, to work together.
Thank you. Is it on? Yes. Do you think it will be possible in the near future to simulate these collision experiments without having the particles actually collide? Maybe a computer can simulate the final output of these particles without you having to actually make them collide, maybe at least at smaller energies.
Well, I wonder if I understand the question properly, but I would argue that is what we are doing. We are simulating these collisions. Of course, the physics, you're right on some level that one is always making approximations, and of course, a lot of this is models. We say, oh, you're talking about a fluid, but that's just a model. I don't have tens of thousands of particles that are interacting with each other, and then this gives out this physics of the fluid. But to some extent, we are simulating it. But if you're asking whether at some point we won't have to do the experiment anymore, we can just run it on a computer, and then we don't have to spend all of this money and
something like that.
Yeah. Yeah.
Because maybe you had the idea to use oxygen, and 6 years later you get after it to it.
Yeah.
So, yeah.
Yeah, it's an interesting question. I don't know. I think that the nature of what we do is not to try to replicate nature. We don't try to replicate nature. We are trying to understand nature. And so it will always be necessary to do the experiment, because you will always run into things you haven't been able to put into your simulation. I think that's maybe just that's a matter of taste. That's how I feel about it. But every time you do these experiments, you learn something new. There's always stuff we don't understand. There's always things we would like to know more about. We've never been able to do something and say, 100%, I get that now. That's perfect. I can put that away. There's always more physics. So yeah.
Yes. Thank you.
Sure.
Okay, so thanks for the presentation. Let me come back to, let's say, more detailed question. In some of your model predictions, you had an RAA that was larger than one, at least in some regions. So that would, if I understand that correctly, that would actually be something like an energy gain. So where would that energy come from?
Right. Okay. So it is a bit of an oversimplification to say, it is something I said, so I should take that back maybe. It's a bit of an oversimplification to say that if the RAA is less than 1, you have energy loss. What the RAA really is, and I'm pretty sure I had it, here's the formula. What the RAA really is the ratio of spectra, of cross-sections, cross-section and AA, that you scale in some way. So if you have a look here, what I've done is I've said how many particles have some momentum in an AA collision, and I take the ratio of that to how many particles have that same momentum in a proton-proton collision. But then I have to scale it by this number, where here I've scaled it by the mean nuclear. Now I'm blanking on it. What you do is you take 2 Wood-Saxons, I'm forgetting the name now. It'll come back to me in a second. You take 2 Wood-Saxons and you overlap them, and you try to argue that, okay, if I've overlapped these 2 Wood-Saxon models of the nucleus, how many 2-to-2 hard scatterings do I create? How many binary nucleon collisions are there? Which allows me to say how different is a lead-lead collision from just 208 proton-proton collisions, right? So this is what this number does. And if you have done this number correctly, then you expect that you get RAA is 1, there's no energy loss. What is difficult is that this number, and it's part of the problem why the RAA is so difficult in proton-lead collisions, is that this number is model dependent. It's a model, it's a statement about a model. So you have to extract that number. You cannot know it. You have to extract this number or model it. And so then you get some variation there. So okay, that's the first statement, is that it's not so obvious that RAA that's not 1 is not energy loss. Now you ask the question, can you get an RAA that's greater than 1? And would this be energy gain? And so for instance, we got this in our prediction here. And where this comes from is that, of course, the energy cannot be lost completely, right? The energy, you always conserve energy. So the energy, when we say the energy is lost, what we really mean is that some of the energy is going into the plasma. You're sort of kicking the plasma around and heating it up. In this model, what you have in this model with this line that goes above 1 is that you get kicks from the medium. So the medium has some temperature, so the particles are moving around. So you're interacting with it. You get some kicks from the medium, which give you an additional transverse momentum. Momentum transfers to the direction that you're traveling in, which increases your momentum. And if you are not able to properly subtract that out of the medium, then it looks like energy gain. So in that sense, it's energy gain. But I agree with you that the physics is getting mixed up there, and that model is not ideal for this particular type of thing. If you have really jets and you can carry the momentum outside of the jet, then this model does perfectly well. Yeah.
Thank you.
Hi, Isobel, nice talk.
Sorry.
I was wondering, it seems like the nuclear structure plays an important role in these predictions. I mean, if you take the lead nucleus, it's nearly spherical, which is not the case for oxygen. So how important is nuclear structure in these calculations?
It's crucial. I'm so glad you asked this question. So I wonder if I have a backup. So here's the slide that I took from someone else at last year's workshop. The nuclear structure is actually really fascinating because when we do the lead nucleus, we have to model it using some essentially really Wood-Saxons, right? Because the lead nucleus, oh my God, sorry. The lead nucleus is up here at 208, yeah? What these yellow dots versus blue dots is the blue dots, the nuclear structure community can actually compute this ab initio. What does that mean? It means that you take only the physics of the interactions of binary nucleon interactions and triple nucleon interactions. So you have a 3 nucleon interaction and a 2 nucleon interaction. You take only that physics and you put it on a supercomputer, and from that you can compute the structure of the nucleus. Now you can see that, which is quite remarkable if you think about it. If you think about the 3-body problem, for instance, right? In principle, you can do that easily with 3 nucleons, but you see that they've gone all the way out to 50 nucleons in some cases. Right? So they can really compute these things now. You really need really, really big computers to do this. But the point is, so that was one of the reasons for doing oxygen, is because the nuclear structure of oxygen can be calculated ab initio. So it's no longer a model input. Having said that, these calculations also differ from each other. There's some systematic error there. And we were able to, well, not we, some colleagues of mine who do this. Oh, I don't have that as a backup slide. Oh, they're going to be so upset with me. Oh, actually, well, okay, so I can make a statement over here. This was the prediction that we had for the RAA. And you see, if you look carefully, you'll see that we have a solid line and a dashed line. And so we've done here oxygen and neon for PGCM and NLEFT. These are 2 different ab initio calculations of the oxygen nucleus. And you can take, if you take the ratio of neon over oxygen, you see very quickly that actually there is the nuclear structure input matters, and that you can actually start to use these kinds of collisions to inform those calculations. So those nuclear structure collision calculations are very interesting. And in fact, I don't know, is it time to talk about this alpha clustering? So alpha clustering is a thing where did I have this? Oh, here. So an alpha particle is a helium nucleus, 2 protons, 2 neutrons. 4, and they sit in this like very nicely tight, it's very strongly bound nucleus. It's the most stable nucleus there is. And it turns out that if you have a nucleus which is a multiple of 4, so 4, 8, 16, 20, which is the oxygen, and then 24, which is 20 is neon. No, yeah, 16 is oxygen and 20 is neon. Yes, sorry. Okay. So 16 is oxygen and 20 is neon. If you have something that's a multiple of 4, it turns out that the ab initio guys realized that you should be, actually what's happening, the best configuration for the nucleus is that it should not, it's not some arbitrary thing of 20 nucleons. They really are 4, so the oxygen is 4 helium nuclei. It's really 4 alpha clusters that are sitting close together. But this is very difficult to measure experimentally. Although it is essentially established, but there's no single experiment that can measure this. It really is several experiments together. And in this, with this run, they have, and maybe, okay, I won't go into the physics of how they managed to discover this. We can chat over dinner because it's actually kind of cool. But the claim is that really they've seen alpha clustering now at the LHC as well, which is, I think that's really cool. That's a low energy nuclear physics question that you see at the LHC. It's kind of cool. Yeah. Yeah, but you see, but it's sort of seen, right? It's not really like, yeah. Now we'll talk a little bit. Okay, let's talk. Yes, exactly. So yeah, and this is the same argument that they made here, is that, okay, but yeah, you have some process which causes alpha particles to get knocked out preferentially, which you then say the only way that you can really explain this is if alpha clustering is a problem. Yeah, is a fact. Yeah, that's very cool. I think it's exciting. Yeah.
Oh yeah, thank you for your presentation. My interest is on your animations. I don't know, is that part of the team that you're working with?
Yeah, like these ones.
No, I see this one. So there's a very specific one that shows how the electrons collide inside.
Oh, no, that's promotional material from CERN.
So I was questioning if
these
which team was behind it.
I can find out for you. I don't immediately know, but this is promotional material that you can get on CERN's website. It's actually this I think got from the Alice guys. Is this Atlas? Now I'm going to say I think it's CMS actually. No, but Zinfir sent me this link. Yeah. So this is produced by the people at CERN, and CERN, because CERN is really, oh, you're right. No, I apologize. No. CERN is really interested in making these kinds of things available to everyone. So it's on their website. They have CERN has a website, and they have many of these kinds of things. They get artists and things in to come and do this. Yeah.
Okay, thank you.
Yeah.
So there are no online questions. So we should thank Dr. Isobel Kolbe for such a wonderful talk and taking us through into things that we learned in physics many years ago. Thank you.
Thank you. Thank you for coming.
We normally have a culture of giving our magazine, Wisaku, which is produced from the mathematics department by Professor Sophie, who is sitting at the back there. And this is the gift for you to enjoy the love of mathematics and the need to popularize the concept of mathematics in education. Thank you. Thank you. I am sure there are some refreshments at the outside there, so we can actually go and speak to the speaker.